start the recording at the beginning of class, but my goal is going to be to record all of these. Sometimes it might be this 1020 version, and sometimes it might be the 1140 version, but I'll generally talk about the same things. But I'll post those here as we go through them. Also, if there's something else you guys are working with or fighting with, and you want me to make a little video about it, like for example, if you're struggling with the stem and leaf plots, it sounds like most of you have found little videos online that have been real helpful. Again, once you get used to using stem and leaf plots, they can be read fairly easily. They're just weird and they take a little bit. But if you want little extra videos on a particular subject, or if I get a bunch of messages or see a bunch of stuff in the forum about a particular type of question and I add in a video, this is the place I'll put it. Okay? So keep that spot in mind for a hopefully real big growing list of videos. I did decide to use the labs that are here, mostly because we won't be able to talk as easily in class, and the labs that are on here already, they do have really nice talk throughs for how to approach them and how to use the Excel tools to do them. Some of them are not quite as in-depth as some of the other things we could do, but we'll supplement those tools so you guys see those tools. But I think it's particularly nice that Svetlana Varner, one of our instructors, went through and built these videos explaining how to do each of the lab pieces. So it's something that you can refer back to and use. So I think we're going to stick with the ones that are here. So if you want to start looking at those and start playing with those, please do. We will play with that lab 1 tomorrow. So tomorrow will be an introduction to that and mostly lab time. So you guys can work on that. Ideally, you guys should be able to finish most of that during that class time. Okay? No.
I had a question about the labs.
Yes, ma'am.
Do we typically do them together as a class, and then after we're done with class, we work on them until we're finished, or can you start them ahead of time?
You can start them ahead of time. If it's a lab day and you've looked over the lab and you're comfortable but want to do it later, go ahead and do that. For the days that have the lab, I will mostly, kind of give an introduction, answer any questions you guys have, and just kind of hang out and be here to answer questions and help you guys with stuff. I can even reset up the Zoom interface on those days, so you can share your screen with me so I can see what you're looking at on your documents, and that might be really helpful as well. This lab 1, I might, if I were all of you, look at it ahead of time, because it does ask you to collect some data. So if you want to collect that data before we meet, that might be handy, because it asks you to essentially go collect some categorical data, some continuous data, and some discrete data. So collecting that ahead of time is probably handy. That all make sense?
Yeah, thank you.
Sure. Okay, let's see. Anything else that you guys have been fighting with or want to look at or ask about or play with?
Actually, I had another question on the homework for 2.3.
Mm-hmm.
There was one question that I was kind of stuck on, and I think I just got too confused that I was getting myself all bunched up. But it's question 2. It has like the 4 parts to it. I got like 3 of them, but 2 of them I kept getting wrong.
Yeah, I was looking at this earlier. I was going to bring this question up, but I had forgotten. So thank you for reminding me. So most of this is just getting used to reading these tables, and also just getting used to how the textbook uses the language and how the problems are going to use the language. And one of the real important things to practice on these is that kind of interpreting these questions. Again, as I said last week, most of what we're going to be doing or focusing on is kind of vocabulary and perspective, not so much mechanics. So there's not going to be a lot. There's going to be some problems. They're going to have some, you know, certainly some math we're going to have to do, but mostly it's going to be understanding what is this question asking, what does this mean. So focus on that as you work. So when we look at your question was presumably your numbers were probably different. But what is the frequency of lottery winners? So this is supposed to be the ages of 30 lottery winners. And we're given a pretty complete frequency table here. We've got some age ranges, the frequency, those are turned into relative frequency, and even cumulative frequency. So for example, notice the cumulative frequencies, they get larger as you go along. So this 0.1333 is all of these for people in that age range. But this next column, that 3 to 39, this cumulative relative frequency of 0.3 is all of these people in that 30s range plus all the people before it. So if you add the 0.1333 to the 0.1667, if you add those together, you get that 0.3. And so on. So this, in the 40s, there were 2 people in their 40s who won the lottery. Their relative frequency was about 6.67%. But again, that cumulative frequency is the sum of them and everybody before them. That cumulative is everybody brought together. So everything from that value down. So this table has a lot of information on it. So if we want the frequency of lottery winners between 19 and 40, I'm just going to go through all of these. I don't know which ones of them were causing you trouble, but I think talking through all of them might be handy. So the frequency of lottery winners between 19 and 40, well, 19 is kind of off of this list. That's okay. That just means, this cumulative frequency is everything before that. So from 19 to 40 is essentially going to be these first 2 columns. Like, yeah, are there 40s in here? Well, this is essentially from 40 up, not quite 50. This is from 30 up. So really this 19 to 40, we're just kind of staying in these first 2 groups. So if we wanted to know how many, well, there were 4 from this group, 5 from this group. So the total frequency should just be that 9. Fair? If we were looking for the relative frequency, since it is just these 2, we could add those 2 relative frequencies together. But because that is the 39 all the way down, we could just use that 0.3 as the sum of those 2. But just wanted the frequency, so we just add those frequencies together. What percentage of lottery winners are 70 or older? So 70 and older is going to be these 2 sections. So from 70 to 89, 70 to off that list. So we could do this a couple of different ways. If we wanted the frequency, that frequency is 6. So we could say 6 out of 30 and go with that. 6 out of 30 is, 6 out of 30 is 1/5, and 1/5 would be 20%. So we could go with 20%. Or we could add these relative frequencies together. So the 0.1667 plus the 0.0333, add those together to get the percentage of lottery winners. Or we could even go one further, and this is actually handy with cumulative relative frequency. If we want to know everything that is from 70 and above, well, this part of the chart is everything less than 70. So this 0.8, that 80%, if 80% is less than 70, then 1 minus 80 is, or 100% minus 80% is 20%. So the rest of this had better add up to 20%. I think we talked yesterday about that 1 minus being handy often. This is one of the places that 1 minus is really handy. Fair? So lots of different ways you could have approached the 70 or older. Either way, we end up with 20%. Did say round to 2 decimal places, so I am going to put in the 2. Sometimes it wants them if they're zeros, sometimes it doesn't. I'm just going to be safe and put them in. Fair? It does have to be 20 as opposed to 0.2 because they did put this percent symbol here and they asked for a percentage, so it should be 20%. If they asked for a proportion, that proportion would be 0.2000. What is the relative frequency of ages under 40? So again, under 40 is those two. It's actually almost the same as this, except this is frequency. They want relative frequency. So these two, the under 40 is cumulative. So really it's just that, oops, that 0.3. Again, we could add those together, get 9 out of 30 and reduce that fraction. Or we could add these two together, get 0.3, or this cumulative relative frequency just tells us the 0.3. So the relative frequency, that shouldn't be a percentage because it's not in percent notation. So it's just going to be the 0.3. It asked for 2 decimal places, so I'm going to give it the 0. You're probably noticing that there's a lot of different ways to read this table for that same information. One of the things about this table, I said they're giving us the same information in 3 different forms. Really, any one of these columns would be complete data. We'd be able to answer any of these questions from any of those 3 columns. Because we're given all of them, we have just so many choices in how we want to pull that data out. If you want to talk about it from the frequency, do that. You want to talk about it from the relative frequency, we can do that. You want to use that cumulative, it's handy for some of them, you can use that. So this is almost an overabundance of information, which can lead to, I think, what you were describing of kind of feeling like, how should I approach this? Because there's just too much information. And that is a problem with this problem. So hopefully it's not sounding like too much because I'm throwing so many options at you. Okay. Let's see, cumulative relative frequency younger than 50. Well, that's nice because we do have that chart for it. So younger than 50 would be these 3, so in the 20s, 30s, and 40s. So if we wanted the cumulative frequency younger than 50, we can just take that cumulative frequency from right there on the table, or we could add those 3 together. Now, I want you to notice something. One of the things that often happens with these is we kind of don't pay attention to some of the details in here. So often we'll just see cumulative frequency and 50. Well, here's a 50, here's a cumulative frequency, so I want the answer to be 0.5667. But that's not what the question asked. Fair? The question asked cumulative frequency younger than 50. Well, younger than 50 is these 3. Fair? It doesn't include that 50 to 59. So we've got to use this number, not that one. Does that make sense? And that's why we want to get in the habit of reading these very carefully, so we know what it is this is asking. 0.37, because we were asked to round to 2. I think most of the ones that I saw who were fighting with this a bit, or who traditionally fight with this a bit, it's this question. They often want it to be this answer. Fair? And the last one, which graph shows relative frequency? Well, our relative frequencies, they start small, they get larger to a max of this 0.2, and then get smaller again. Well, this one kind of does that. So at 20, well, in the age range of 20, we're somewhere between 0.1 and 0.15, and that's where we are. 30 to 40, we are a little above 0.15. So 30 to 40, we're a little above 0.15. So that looks like it's matching up. Notice this one is increasing the whole way, right? We certainly didn't have like 100% of this data between 80 and 90, but the cumulative relative frequency for 80 and 90 was starting to get near 100%. So this one is cumulative frequency. This one is relative frequency. We're asked for which graph shows the cumulative relative frequency. So we do want this one. Is that fair? So yeah, there's a lot of meat in this question. And that's one of the reasons I like this question, is it is very particular about, you've got to make sure you're reading those and looking at the olders and the youngers and interpreting these intervals carefully. Allie, that help? Okay. Anybody have any questions about those?
Thank you.
Sure. I'm curious, did I get them right? Ha ha ha. I don't always. Often it's little rounding issues. So I wonder if I hadn't put those zeros there, would it have gotten mad at me? Oh, no, apparently not. Okay. Do be careful about those rounding issues, though. I always think, when in doubt, if it told us to go to 2 decimals, go to 2 decimals. Cool. Anything else from the homework, or anything else that you guys have been working on that you want to look at? Okay. Then let's look at what I want to talk about today. Let's see, I want to move that over here, actually. But I have learned when I do that, it yells at me, so. Boom. So did that work? Do I have the big whiteboard up there for you? Okay. Okay, so what I want to talk about today is measures of center. Measures of center. Now, measures of center is a very formal term. We often just use the word average. Get my brain to work today. So when we talk about something's average, we're talking about distilling a list down to a single element, a single value, a single category that's going to stand for everything in a big list. When we talk about it in terms of measure of center, if it's a big spread out bunch of data, that average is about where is the middle of that data, where's the center of that data. So it's all, nice to, falls under the general category of average. The problem with the word average is that there are several different kinds of average. For example, if I give us some data here, say 4, 3, 9, 1, 7, and 14, say, it's what, 1, 2, 3, 4, 5, 6. I want one more here. And how about 5? So 1, 2, 3, 4, 5, 6, 7 data points. So if we had this set of data, the curly brackets, by the way, in mathematics, we don't call them curly brackets in mathematics. Frankly, a lot of us do, but they're technically referred to as set brackets. So this is the set of data 4, 3, 9, 1, 7, 14, and 5. So if I asked you to find the average of this set of numbers, what most people generally do, and what you probably do, is add them up and divide by how many there are. Is that right? Is that what you would go to when asked average? Seeing a couple guesses.
Yes.
Good. So take a minute and do that. Find that average of these values, add them up, and divide by how many? 4 plus 3. And I'll give you a minute to do that. Does that add up to 43? Is that right?
Yep.
Cool. 43 divided by 7.
6.1.
Oh, nice. So about 6.1, you said?
Yeah.
Cool. Now, some notation here. If we call these data points X, where, the big solid line where, or such that technically. So X such that X is equal to these values. We will often see it written as sigma X. This is the Greek capital letter sigma. It's essentially what in Roman letters is an S. So this stands for the sum of. So the sum of all these X values. It's just a shorthand for writing add them all up. So sum up those X values and divide by how many there are. We will generally use N as our variable or as our symbol for the number of elements. So you'll see your book use this notation, and I'll use this notation a fair amount, and it just translates into the sum of all the values divided by the number of values. Exactly what we have up here. Add them up, divide by how many. Just in really shorthand notation. So that we found was about 6.1. And hopefully that number 6.1 seems reasonable. Most of these numbers are, 1, 2, 3, 4. Oh, there's no 2, sorry. 1, 3, 4, 5, 7. There is this 9 and 14 pulling that average up a bit. But 6.1 shouldn't seem like it's crazy for the middle of this data. Now, 6.1 isn't one of the actual data points, and that's okay. It's just standing for, on average, what all of that is. Now, this average is actually only one of a number of different types of average. Anybody know or remember what this type of average is formally called?
Mean.
Perfect. This is called the mean average. And the symbol that we will often use for it is X bar. X with a little bar on top of it. It really is technically pronounced X bar as a symbol. But that X bar is the symbol that we will use for a mean average. So really, when somebody says average, they're often thinking of this type of average. When you tell people find an average, this is usually what they jump to. But it really is only one of a bunch of different kinds. We'll focus on 3 of them, but only a type of average. So really the good response, if somebody says, here's some data, find the average, the good response would be, well, which one do you want? What type of average? Fair? So one of the things I want you to kind of disconnect is the connection between average and this behavior. Average, which type? Oh, I want the mean average. Okay, the mean average means add them all up, divide by how many? That nice 6.1. Fair? Well, if that's just one type, there had better be some other types, and there are. One of the other averages that we will deal with a lot, and that you actually hear a lot nowadays especially, is the median average. If you think about where you've heard the word median, it's a lot like medium, of course, which is the middle size in things. But the median strip on the road is that strip down the center of the road. Median really comes from the Latin root for middle or center. So it's a different way of measuring center than the mean average. And the way we find the median is, first and foremost, we have to put our data in order. So median requires ordered data. So this 4, 3, 9, 1, 7, 14, 5 is fine for adding them up and finding the mean, but to find a median, we really want to have this data in order. So in order, it would be what? 1, 3, 4, 5, 7, make sure I don't miss one, 9, 14. 1, 2, 3, 4, 5, 6, 7. Good. So that's our ordered set. Which I really don't want the brackets there. Sets don't have to be ordered. So we're changing this into an ordered set, so I don't want the brackets. One of the nice things about Excel when we use Excel is great at doing this. If you have a data set, a crazy misordered data set, highlight that data set, hit sort, it'll order it for you. So for big sets of data, we don't have to do this by hand a lot. Excel will do it for us. So if we want the median of a data set, it really is literally just that data point in the middle. It is the data point in the center. No adding, no dividing, no nothing. We just grab the point in the middle. So for this data, the median, we don't have a symbol for median quite yet, but we'll get one, like I think early next week, maybe the end of this week. But for right now, we'll just call it the median. Here, the median is 5. So our 2 different types of average do give us a different result. And oftentimes they do give us different results. Really, they should give us different results because they're trying to measure different things. For numerical data, these will be our big two different types of average. And I want to spend a little bit of time talking about why they're both important and what really makes them different. But before we do that, any questions about what I mean? Got to be careful about using that word now. By questions about either of these ideas. What if there are two numbers in the middle for the median? That is an excellent question. So I did purposefully make this list length 7, so I had a middle point. But let's say I didn't. Let's say, oops. Let's say the world wasn't as kind and we had a data set. I'm going to write it in order just for our convenience. 2, 3, 3, 9, 11, 12, 14, and 87. It's 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 data points in order. So if we tried to take the data point in the middle, well, 1, 2, 3, there isn't a middle. The middle is these two. And I don't want my median to be two different numbers. I want a single value for that median. So what are we going to do with those two numbers to try to get a center between them? Well, 9 and 11 is actually pretty handy. If we try to think of, well, what's between 9 and 11, there should be a number that jumps out at us. But essentially, it might seem counterintuitive, but to find the median, if there are two middle points, we essentially find their mean. That would be 20 over 2, so it would be 10. So here our median would be 10. So if ever the list is even, there's always going to be two numbers that try to be the middle. So if you have an even numbered list, we just take those two in the middle, find their mean, that's our median. If there's an odd number, there's going to be one in the middle, and that's our median. Darby, does that make sense? Cool. I know it is a little bit weird that we're finding the median, so why do we do a mean in the middle of that? But as we talk about the distinction between the two, that should clear it up a bit. So why do we need both of these? Where they really are finding the center, finding the middle in very different ways. Because the mean has us add up the values, the particular values up here matter a lot. Particularly notice here, this 14. That 14 was quite a bit higher than most of these. Okay, it was fairly close to the 9, but really that 14 was quite a bit higher than most of these other numbers. But when we added them together, that 43 is kind of bigger than it might otherwise be because this 14 added so much. So when we divided it by how many we had, 7, that's 6.1. Notice it's higher than that 5 because it took into account this high value. Fair? Imagine if instead of 14, imagine this one number had been 497. Okay, then we'd have 4 plus 3 plus 9 plus 1 plus 7 plus 497 plus 5. So that would give us, 500 and something. 500 and something divided by 7 is still near 100. That would give us a mean of something in the hundreds. So the mean is very affected by really large values, or correspondingly really small values. If these were all in the hundreds, except for this was still just a 1, that 1 would pull us way far away from those big numbers. So because mean cares so much about the values, weird values can throw it off. For example, Darby's question brought up this other set. If we found the mean of this other set, this 87, it kind of stood out, didn't it, when I wrote them out?
Especially since it looks like a 27.
Well, okay, I'm still getting used to writing this on this board. But that 87 should have stood out. It is a very large number compared to the rest of these. It's an extreme data point in comparison to the rest of these. If we added these up and divided by 8, we'd get a much higher value than this. Fair? So the mean is easily skewed. That word came up in your reading and will continue to come up. The mean is quite easily skewed by larger values, or correspondingly by smaller values. Whereas the median doesn't care about the individual values. All it cares about is the order that they're in. So we often think of the mean as an average by value, because the values really do guide the numbers when you're finding a mean, and the median is instead an average by position. It's the center value, it's our average value because of the position that it's in the middle. Notice here, the fact that that 14 is a 14 doesn't affect this 5 at all, except for the fact that it's the last one in our order. If we changed this to that 497, it wouldn't change the median at all. Heck, we could change this 9 to a 105. Doesn't change the median at all. But those changes would certainly affect our mean quite dramatically. Right? Now, why is this important? We usually use the mean average. Again, when we think about average, we often work with the mean because, values are important. How much the large numbers affect what's going on, or the small numbers affect what's going on, is often important. But there are times when that mean will really misrepresent the data. I'll give you an example. If you look at, don't look at that H. If you look at home prices in the area, so you might find some homes that are, say, 150,000. You might find some homes that are 220,000. You'll might find some homes that are 315,000. Find another ones that are 185. You might find some that are less. Not be hard in this market, but you might find some that are lesser. You might find one. So you'll find a bunch of different home prices, and you want to know, okay, what's the average home price? Well, you might not look at them, but if you do some searches, there are home prices that are obnoxious. So 2,000K, this is a $2 million home. Now, there aren't a lot of $2 million homes in the Rogue Valley. We can think that's either good or bad, but if we were to take, there's even some way up in those hills that are, closer to 10 million. So if we had a whole bunch of these, fairly reasonable home prices, and a couple of these really expensive homes that, like, these are not, the normal homes that people buy in this valley. But if we were to average these and find a mean, what's going to happen with this $10 million house and this $2 million house? It's going to take our average and make it look much, much larger than it would otherwise be. Does that make sense? And people will often use that. They'll say things like, the average home price in Medford has gone up a whole bunch to try to make the area look really good. And they'll go, okay, yeah, the mean has gone up because they built a couple of $10 million houses out there, but that doesn't affect the rest of us. For the rest of us, these reasonable homes, those prices have stayed fixed. So which is more important? The average by value, taking into account these big ones, or if we listed these in order, wish I hadn't made those dots there. I'm trying to get rid of it. If we list these in order instead, and just grab the one in the middle, let's see, that would be the first one, and then the second one, the third one. If I get this order wrong, yell at me. That's why it's good to have Excel to just order it for you. Oop, nope, that was supposed to be 6. So that's 7, and then 8 and 9. So if we look at the order, out of 9, which one's going to be our median? Well, 9 divided by 2 would be 4.5. Well, 4.5, actually, we generally take we have a rule here, take n plus 1 divided by 2 to find the middle value. So 9 plus 1 divided by 2 is 10 divided by 2 is 5. So 5 is the central value. So 1, 2, 3, 4, 5. This 225K, that would be our median. $225,000 home. And considering all of these values, this is probably a much better answer to, if you're buying a home in Medford, what's the kind of average price you'd expect to pay? This 225K is probably a much better answer than if we'd have found a mean average by adding all these up. I even kind of want to do that to compare them. So let's take that 10 million and the 2.45 million. And why am I writing these down again? They're all right here. Add all these up, divide by 9, and tell me what you get for the mean. I got to remind myself. I can have you guys do stuff.
What is number 8?
8 is 2450. If you need me to write larger, let me know and I'll try to get in the habit.
$13,874,000.
And then you got to divide that by 9.
1541.5.
Sorry, what?
1541.5.
0.5K. I'm just going to round it to that. I've been doing K for the thousands. So that's $1.5 million. So that's a mean average. You add all these up, divide by 9, you get an average of $1.5 million. Is $1.5 million the average price of these homes?
May as well be.
Well, it technically is. It is the mean average. Is it representative of what the kind of middle of the pack house price on this list? Not at all. It's very skewed towards that obnoxious house up on the hill. So the reason that we have a couple of different types of average is exactly to handle this type of scenario. When you have extreme values out there, the idea of average can get very skewed, very pulled by those extreme values. So sometimes average by value isn't what we want. It's misrepresentative. Where average by position, this 225K for the median, is much more helpful, much more representative. You also hear this in terms of income. When you talk about, the average person who works for a company, what's their income? Well, if everybody at the company is making $10 an hour, except for the CEO who's making $1 billion a year, and you add all those up and divide, it'll look like, oh, everybody's making good money there. But if you've got 1,000 employees making $10 an hour and one person making $1 billion a year, the average employee there is making $10 an hour. Does that make sense? So you can really manipulate data by which one of these you're talking about. You often hear, like politicians will argue that, hey, our policies are working. The average income in our state has gone up by 10%. And then their opponent will say, those plans aren't working. The average income has actually dropped by 5%. Well, how can they both be, how can that both of those be true? One of them is lying, right? Not necessarily. If one of them is saying, hey, our tools are working, the mean average has gone up 10%. Okay, the mean average has gone up 10%. Great. The opponent says, oh, the median is actually dropping. That means that the values, the mean, is increasing because there are big numbers getting bigger, but the middle of the road values are dropping. So it's very possible for one of these to go up while the other one goes down, particularly when, the rich get richer, the mean's going to go up. As the poor get poorer, the median's going to go down. So which average you're looking at can really skew the information. That's one of the reasons, one of the big things you want as a takeaway from this class is that when people tell you things like the average is doing this, you don't just take that at face value. You ask yourself, well, which type of average and what are they trying to communicate to me? Fair? Now, I want you to keep an ear out for this when you're listening to the news or reading things. You'll often, particularly nowadays, 10 years ago, it almost never happened. But nowadays, whenever you hear things about income or home price especially, you'll often hear them say the median home price or the median income, because they're trying to be more specific and more clear. But you'll hear some other, less reputable organizations, or less reputable because they're trying to trick you, or just less sophisticated, just still say average. And in some ways, that's not anywhere near as good information because we don't know what kind of average. All that makes sense? Any questions about that before we talk about the third kind? I didn't forget the third kind. There is one more. I like that orange. I don't know why. By the way, if any of you are colorblind, particularly the red-green colorblind, sometimes it's hard to see the reds or the greens or, depending on what kind of issues you have. If any of the colors are problematic, or if all the colors are problematic, do let me know. I had somebody in class once who couldn't see green markers. It was this kind of light fuzzy gray, and anytime I wrote in green markers, he could not see what I wrote. He didn't tell me that until week 9. Let me know. I'm happy to try to remember not to or adapt, but do let me know. I felt terrible, but at the same time I was like, what's wrong with you? You gotta tell us these things. But then I felt bad because what's wrong with me is I'm colorblind anyway. So just let me know. You don't have to let me know here. If you want to just send me an email or keep it private, that's great, but let me know. So the other type of average is for questions like, what type of soda does the average, let's go McDonald's, well, I'm not going to write it out, McDonald's customer order? So if we imagine somebody wanting to know what type of soda does the average McDonald's customer order, and of course, McDonald's certainly wants to know that. Advertisers want to know that. Suppliers want to know that. So wanting to know what type of soda the average customer orders is an important type of question. And of course, if you made a list of orders, you might have, Sprite, Dr. Pepper, Coke, probably more Coke, Diet Coke. You could make that looks weird. You could make a big list of different sodas that are ordered. But if you want to find an average, well, a mean would be, okay, add them up, divide by how many sodas were ordered. What is Sprite plus Dr. Pepper plus Coke? You can't add them up. It doesn't make any sense. So the mean automatically is out the door. We can't add them up and divide. That doesn't make any sense. To find the median, we'd have to put them in order. They don't have an order. They don't have numerical value. So, what goes first? Sprite, Dr. Pepper, Diet Coke. There isn't an order to it. So if we can't add because we don't have meaningful numerical values, if we can't find a median because ordering the list doesn't make any sense, then we're stuck with this third type. What do you think we could use to say what the average is when we can't add them up or can't order them? What other tool might we use to say, hey, this is the one we're going to call average? Any thoughts?
Would be like frequency.
Cool. So we could look at the frequency. If we look at frequency, which one would you say would be the average?
I don't know, Coke maybe.
Well, it is, but looking at frequency, you'd specifically be looking for the one with the highest frequency, right?
Yeah.
That's what you meant by look at frequency. So look at the one with the highest frequency. That's why that looked weird. I forgot the R. And we call that the mode average. People often think of it as the most common of the data points. Now, sometimes there isn't a particular data point that has a really high frequency, or there isn't a particular value that is significantly higher or even higher at all than the other values. Like this list here, no value on this list comes up any more often than any other value. So it wouldn't have a mode. That's okay. Some lists just don't have modes. But in general, if we want to find a mode average, we do look exactly what you said. We look at that highest frequency, that most common data point, and that is our average. And if you are curious, for McDonald's sodas, you are right. It is Coke, is the mode. But we certainly don't get there by adding them together. You can't. Now, why do we use the mode sometimes instead of mean and median? Well, exactly for this reason. It really is our measure of central tendency for categorical data. When we have data that doesn't have meaningful numerical values, we can't find a mean, we can't find a median. Mode is all we got. So usually we're using it because we don't have any other option. But there are other purposes. Like if you wanted to carry, say, that's a weird example, but for some reason that's what popped into my head. If you were going to, sell shoes and you could only get one size, well, you'd want to know what the most common size was, right? You wouldn't be worrying about averaging them. If you only had to pick one, you'd pick the one with the highest frequency, you'd pick the mode. I don't think that's my best mode numerical example, but for the most part, we will be using mean and median because we are going to stick with primarily numerical data because it's more interesting. But that mode will come up fairly often. And every once in a while, by the way, you get a question about, what's a scenario where mean would be better than median, or what's a scenario where median would be better than mean. Those are usually about, skewed values. The question of when is mode the better one to use, the general answer is anytime you have categorical data. Anytime you don't have numbers. Before I let you go, there's one more thing I want to mention. We refer to descriptive statistics like median as being resistant. Ooh, is that an E or an A? I'm going to pretend it's an E.
A.
It's an A. Okay, I was wrong. Those of you who don't know me from other classes will learn very fast I cannot spell to save my life. So it's going to happen someday. Somebody's going to go, spell this or I'll shoot. And I'll have lived a good life. It'll be okay. Hopefully it won't bother you too much. Feel free to correct me. That's the only way I'm going to learn, right? So resistant. We refer to median and measures descriptive statistics like median as resistant because it is resistant to extreme data. It's resistant to really high or really low values. So when we have highly skewed data, we often like to use resistant measures. Mean would be non-resistant because it is highly affected by extreme values. So every once in a while, your homework will ask you about resistance or ask you to put something in terms of resistance. What it's referring to about a resistant measure is whether or not it's affected by extreme data. Cool? Any questions about any of that? We'll play with some of these tools a bit, but that's the spiel on averages. Hopefully that widened your view of what it means to be an average a bit. All right. Go forth and play with that. If you do have any questions or come up with anything you need, let me know. And have a wonderful day.
Thank you.
You're welcome. We do have the 1140 class starting in, sorry, 1140? Yeah, 1140 class starting in a little while. No. Is it 1140? Yeah, it's 1140. So we'll start that in a little bit for those of you who are hanging around. And I will come back in a minute and do that. Let me stop that recording.